Hello students, good evening. We have once more arrived at the physics class. So we are preparing for NEET physics, right? So you must have understood, like for NEET, the biology portion is the maximum and physics and chemistry, they are 50% of biology, right? The thing is that you will be having maximum numerical problems and you have to solve them very quickly. The key point of solving NEET is the conceptually you need to be very strong, but one thing for sure, the questions will not be very difficult. It's not like that. The mostly you will see the concepts you have to directly approach. Like you have seen in the last class that I took, right, on laws of motion. Like you have the questions, the calculation to is also very less. Directly you have to answer the concept and use a formula, right? So today the topic we will discuss is properties of solids and liquids. Now what properties I'm talking about or will be discussing, that is nothing but we'll be mostly discussing on the mechanical properties of solids, mechanical properties of fluids, and thermal properties of matter. Okay, now what are the mechanical properties of solids? Basically, mechanical properties of solids are, what is happening? Are elasticity. In elasticity, you have three kinds of elasticity. One is the Young's modulus, one is the bulk modulus, right? You have all these. Okay, mechanical elasticity basically will also study about springs, spring constant, right? For mechanical properties of fluids, we have three things basically. That is, for fluids, we will consider fluid at rest. At rest, we have to know about the pressure and problems on Archimedes principle, flotation. And also, when the fluid is in motion, then we have to know about Bernoulli's theory, Bernoulli's equation, right? Viscosity and surface tension. Though surface tension comes under fluid at rest, right? Surface tension. So all these things will be covering through small problems. And thermal properties of matter. Basically, we deal with thermometry. Then what you have? You have conductions through solids. Then we have radiation. Convection, those kind of things are mostly, they are more theoretical. We don't have much mathematical problems, right? So this is the overview of the problems we'll be dealing today. So let's start with our first problem. Okay, first problem I'm reading. When a weight of 10 kg is suspended from a copper wire of length 3 meter and diameter 0.4 millimeter. The copper wire is of length 3 meter and the diameter is of 0.4 millimeter. We need to keep in mind the units. Its length increases by 2.4 centimeter, right? If the diameter of the wire is doubled, then the extension in its length will be, right? See, while first if you see the problem, you will, you can think like you have to have the Young's modulus, right? Young's modulus of the wire. You have to calculate and then you have to find out the length, the new extension. But that will become too long. see how we are using the formula so that we can have a relation between the diameter and the length. See, what formula we know? First of all, Young's modulus, or the modulus of elasticity, is nothing but stress by strain, right? Now stress by strain, stress is nothing but the force by unit area, and strain is nothing but the ratio between the extension and the original length. So del L by L, which we can write FL, this del L into A. Now see, for this problem, we are not changing the wire. So when the wire is not changed, then this is constant, this is constant. When a weight of 10 kg is suspended, see, we haven't talked about the weight later on. So weight is also constant, that is the force is constant, right? And suspended from a copper wire of length 3 meter. Length is also constant. Its length increases by, see, the diameter of the wire is doubled. So we are not changing the length. So these things are constant. So see, if we take the constants in one side and bring the variables in the other side, so we can write del L A equals to F L by Y, which is a constant. This thing is a constant in this problem, right? Now what is A? A wire is definitely the cross section of the wire is a circular in shape. So it's nothing but pi r square. R square is nothing but the radius, so it is pi d square by 4. So we can write del L pi d square by 4 equal to this, say this is a constant k. Now in this, pi and 4, these are also constant. So if you take in the other side, we can write del L into d square is nothing but k into 4 by pi, that is nothing but another constant. So what we have derived in this? We have derived that the product of the extension and the square of the diameter is a constant for this problem, for this particular situation. So we can write, see, when the weight of 10 kg and the length of 3 meter, as it is not necessary here, we would not consider this. And diameter of 0.4 millimeter, its length increases by 2.4 centimeter. If the diameter of the wire is doubled, then the extension in it will be. So, suppose in first, the length of the extension is del L1 and the diameter is D1. So D1 square I write. Del L1 into D1 square. Next, the diameter of the wire is doubled. So, we need to find out the extension in the next part. In the next case. So that is del L2 and the diameter will be, diameter is doubled, right? So it is nothing but 2D1 whole square. Now see, just with the question, I'm using only variables. I'm not actually putting the values, right? Because a diameter is doubled, we don't need to consider about the actual value of the diameter. They will cancel out. See what happens then? Then del L2, this becomes 4D1 square. So D1 square cancels out. This is 2, right? So del L2 becomes del L1 by 4. Now what is del L1? Del L1 is nothing but increases by 2.4 centimeter. So it is 2.4 divided by 4, that is 0.6 centimeter. So by how much, what will be the extension? It will be nothing but 0.6 centimeter, which is the answer. Observe one thing. When you first looked at the problem, what did you feel? That so many numbers are there, so it will involve a lot of calculations. But actually, the calculation is only at this part. So there is no calculation, practically, right? Everything is nothing but the concept. What we did, we tried to find out what is the relationship between the variables which are changing. The others we are just taking constant. And finally, here also, as it is said, the diameter is doubled, we don't need to bother about the actual value. We can directly get the value of the extension. Understood? Fine. We are moving on to the next problem. Okay. See this problem. Figure shows a uniform rod of length 30 centimeter having a mass of 3 kg. The length is 30. The length is 30 and the mass is of 3 kg. The string shown in the figure, this is actually magnified a picture of a string, right? So they are referring to this string, are pulled by constant forces of 20 Newton in this direction and 32 Newton in this direction. Find the force exerted by 20 centimeter part of the rod on the 10 centimeter part. It's actually a problem of Newton's laws of motion, but the thing is that as we are talking about stress and strain and internal forces, right? So we have considered this question to be a part of the mechanical properties of solid, right? Now see, before going into the internal forces, let us first try to understand what is the dynamics of the body as a whole, right? As a whole, see, if we don't consider this one, the internal forces of the body, we can think the body as a point object, and there are two forces, right? One is 32, one is 20. So the net force is what? The F net is nothing but, it is 12 Newton in this direction, right? Now, there is a net force, so there will be some acceleration, right? What is the acceleration? Acceleration is nothing but force, that is 12 Newton, divided by the mass. Mass is how much? 3 kg. That is 4 meter per second square. So 4 meter per second square is the acceleration of the whole body together. And when the whole body is moving in acceleration together, it means all the parts of the body is moving at this, is having the same acceleration. So definitely what will happen, the force that this 20 centimeter will give on this part, see, find the force exerted by 20 centimeter part of the rod on the 10 centimeter part. So we are trying to find out what is the force given by this part on this part. See, if we draw the free body diagram of this part, it is the 10 centimeter part. Okay, 1/3 of this whole block. This is 20 Newton. This force we don't know. This force we need to calculate. Right? How will we find? Now, the parts of the body is also moving with this acceleration. So definitely, with the Newton's laws of motion, we can say the net force on this body will produce the same acceleration. That is F minus 20 will be equals to, what is the mass of this? This is 1/3 of the whole block. So it is nothing but 1 kg. So 1 into the acceleration, that is 4. Right. So what is F? F equals to 24 Newton. Got it? Okay. Now let us think in the other way. Now this part is pulling this part with a force of 24 Newton. Got it? Now by Newton's third law of motion, we can say that definitely this small part, that is 10 centimeter part, is also pulling this part also with a force of 24 Newton. Let us see whether our assumption is right. So if we now consider this 20 centimeter block, right? What are the two forces acting on the block? One is 32 Newton in the right direction and one is 24 Newton in the left direction. The net force acting on this is what? 8 Newton. And what is the mass of this block? That is nothing but 2 kg. Because the whole block is 3 kg, So 2/3 will be 2 kg. So 8 divided by 2 is nothing but 4 meter per second square. And so this part is also moving with an acceleration of 4 meter per second square. Got the point? So though this problem is basically we are applying the formula of the Newton's laws of motion, but as we are talking about the internal forces, stress and strain, so now we can see we can modify the problem, right? If we consider the cross-sectional area at this juncture, we can find out the stress. And suppose there were another string attached in between, right? We can think of like, and it is said like it is of a material which have a breaking stress of this Newton. Calculate so and so. So we can modify this problem to include the mechanical properties of solids too. Okay? We are moving on to the next question. Let's take a water break. Okay, this is a very interesting question because, see, the spring constant, right? You're observing springs, right? So F equals to minus kx. This formula, and like energy, that is a stored energy, is nothing but half kx square. All these things are very necessary for this. And also we will discuss the same similar things in simple harmonic motion. Okay. And so let us try to understand this one. See, there is a mass m. 3 springs are there, k, k, and k. This is 90, this is 135. And as it is symmetrical, this is also 135. Right? A particle of mass m is attached to 3 identical massless springs of spring constant k as shown. The time period of vertical oscillation of the particles. Now the question is, if we just displace it, so with what frequency of vibration, right? This, or what is the time period of vibration for this particle, right? Now, see, it's a combination of spring, so definitely we have to find out the resultant k, right, or the combination, the spring constant of the combination, right? See what happens. First, let us forget about this. If this particle, which is having 3 springs, is pulled, if you forget about this, this is applying a force, right? Let us do it in a separate page. We're trying to spring. Don't think they are resistances. We're talking about springs only, right? Right. Now see, this particle, this force, for this force, say this is A, this is B, this is C. So FA will be nothing but, say, the displacement is y minus ky. Okay? Okay, minus means the restoring force. Fine, it is a restoring force. Okay, now suppose this is also, this FB towards this is also the same, minus ky, but we have to calculate the displacement and the force in the y direction, right? So what will happen? This in this direction will be what? The extension is in this direction, right? So the extension we are calculating in this direction. So we have to calculate the component of extension in this direction, isn't it? Now see, this is 90, this is 135, 135. So I mean this angle is nothing but 45, right? And so it will be what? Minus ky dash, right? Y dash is nothing but y cos 45, because we are taking this component. Now y, the extension, we have taken this component. we have to, at the same time, we have to take the component of the force also. Fine, we have to take the component of force also. So this FB and FC both will have a component in this direction. So what we can say, the F net is nothing but FA plus FB and FC, they are symmetrical. So if we calculate for 1 and multiply by 2, they will suffice our purpose. That is 2, say FB, right? FB, yes, cos of 45, because we are taking the component of force in this direction. The FB itself, it is FA. FA, if we just ignore this sign, if we just write KY plus 2 FB cos 45. What is FB? FB is nothing but KY dash. FB is nothing but KY dash cos 45 equals to KY plus 2K. Y dash is again Y cos 45. That is Y cos square 45. Got the point? Now see, cos square 45. Cos 45 is how much? Cos 45 is 1 by root 2. So cos square 45 is half. So cos square 45 will be, then just it will be half. 1 by 2. So 2 1 by 2, it cancels out. So it becomes ky plus 2ky into half. Half of cancels out. So 2ky, it becomes 2ky. Understand? The force net equals to 2ky. What we have assumed, we have just ignored the minus sign for this because we just want to know the just the numerical value or the actual value, right? Not the sign. So FA, that is F net, if we write 2ky, so what do we understand from this? That is, so the 2k is nothing but the combined spring constant. So this 2k is nothing but the combined spring constant. So basically, the k dash is 2k. The combination spring constant of this combination is nothing but 2k. So what will be the answer? Right? In place of k, you know the formula, right? 2 pi divided by m by k. In place of k, what will you use? Nothing but 2k. So this will be our answer. 2 pi, it's not m by k. It is 2 pi m by 2k. No tricky. Understood? This is a little bit tricky question. You need to understand that we are taking the component of not only the forces but also the displacement. First we are taking the component of the displacement and next we are taking the component of the force. Clear? Okay. We're moving on to the next question. Okay. Now a question from graphs. Let us read the question first. The adjacent graph shows the extension del L of a wire. See, this is the del L of length 1 meter. So this is L, suspended from the top of a roof at one end with a load W connected to the other end. Load W. See, this is load W which is given. So the load W is not constant, but it is varying. Right? If the cross-sectional area of the wire is this, 10 to the power minus 6 meters squared, calculate the Young's modulus of the material. So here we are actually finding out the Young's modulus. Now see so it can be a very simple question, but here what we have to interpret is nothing but the graph. The graph, see, first of all, the weight is varying 20, 40, 60, 80, and the extension is also varying like 1 unit, 2 unit, 3 unit, 4 unit. So it is in a straight line. right? You know that within the elastic limit, it is nothing but the Hooke's law. The load and the extension, they are proportional to one another. After that, it becomes plastic and there are other things. But if we want to find out this, what we have to see, don't see so many things. Just see, because of this extension, this load, this 20 to 40, the extension is 1 to 2 and the slope is constant. So we can say for any change in weight, say we say the change of weight is how much? 20 Newton. So we take 20 Newton. It is nothing but the force. Weight is nothing but the force. And the extension, the corresponding extension is 1. 2 to 1 means 1. 1 into 10 to the power minus 4 meter. Right? Force. And what is given? Area. Area is given 10 to the power minus 6 meter square. Right? And length, L is given 1 meter. So we'll find out first the stress. Stress is nothing but force by area. So 20 by 10 to the power minus 6. So it is nothing but 20 into 10 to the power 6 Newton per meter square. And what is del L by L? Is the strain. Strain is del L by L is nothing but 10 to the power minus 4 meter. Sorry, it's not meter. It is having no unit. Okay. So Young's modulus is what? The Young's modulus is nothing but stress by strain. Stress is 20 into 10 to the power 6 divided by 10 to the power minus 4, right? So it becomes, it is 20 into 10 to the power minus 4, it becomes 10 to the power 10. 20 into 10 to the power 10, that is 2 into 10 to the power 11 Newton per meter square. Which you know, this 10 to the power 11 Newton per meter square is the standard unit or order of the Young's modulus of many of the methods. It is nothing but 2 into 10 to the power minus 11, right? This is my right answer. This is very simple, but only thing is that we have to interpret the graph, right? Okay. Okay. Till now, we were mostly dealing with mechanical properties of solids. Now we'll be coming to, we'll be basically dealing with mechanical properties of solid, and not only that, we have talked about Young's modulus. But now this question will be having something to do with the bulk modulus. Let us read. When a sphere is taken to bottom of sea 1 kilometer deep, it contracts by 0.01%. What do we mean by this word contracts? That is, what happens, first try to imagine, understand. A sphere is taken to a bottom of a sea, means if we take the sphere at the bottom, pressure is increasing. As the pressure increases, the volume is decreasing. The volume, so it is contracting. So it contracts by 0.01%. It means the ratio of the change in volume and the original volume is nothing but 0.01%. So we can write with this del V by V equals to 0.01%. It means what? 0.01 divided by 100 into 10 to the minus 2. That is actually 10 to the power minus 2 to the power minus 4 is the ratio. That is, when a sphere is taken to the bottom of the sea 1 kilometer deep, this is the change, that is the ratio of change in volume by original volume is nothing but 10 to the power minus 4. The bulk modulus of elasticity of the sphere is given by, so we have to find out the bulk modulus. Now what is bulk modulus? See, when we talk about modulus of elasticity for a longitudinal object where the length is predominating than the cross section, we talk about Young's modulus. But when we talk about a volume, right, then we consider that is nothing but the bulk modulus. For calculating bulk modulus, the stress is nothing but the pressure. So we know bulk modulus is nothing but the stress is here is pressure divided by del V by V. Only one thing is that say del V by V, when pressure increases, volume decreases, contracts. So there is a negative sign. But for now, for the time being, we are not considering any negative sign. We are just trying to find out the numerical value. Now see, del V by V we have already found. So we have to find out the pressure. How will we find out the pressure? Yes, we are moving from mechanical properties of solids to mechanical properties of liquids. Means we are trying to find out the liquid pressure. A sphere is taken to a bottom of a sea. So at the bottom of sea, 1 kilometer deep, there will be water pressure, right? What is that pressure? P is, you know, water pressure is nothing but H rho G. H is what? 1 kilometer. So in meter it is 1000 meters. Okay, density of water is given 1 gram per centimeter cube. But usually what happens in a sea, the density is a little bit more than this. But for our, simplification of the calculation, we have taken 1 gram per cc. It is 1 into water, 1 gram per cc. So it means what? Now everything we are trying to find out in SI system. So 1 gram per cc will also be is nothing but 1000 kg per meter cube. So density will be also 1000 here, right? Into gravity. G is nothing but 9.8. So it is, pressure is coming 9.8 into 10 to the power 6. It will be Newton per meter square, that is Pascal, right? So finally, what will be the bulk modulus? Is this pressure divided by this ratio of volume. So if it goes 10 to the power minus 4 goes up, it will be nothing but 9.8 into 10 to the power 10, right? Newton per meter square. Let us see if we have 9.8 to 10 to the power 10 Newton per meter square. Don't get confused. Here is 0.98 into the power 10. There is 8.4, leave. So it is nothing but this. So answer is A. Clear? So here only thing is that we have to understand the bulk modulus means pressure by del V by V. So del V by V is coming from 0.01% and P is nothing but the liquid pressure. Okay, fine. We're moving on to the next problem. Okay. This is a type of problem. You will get plenty of problems like this in YouTube. We are using the similar H rho G principle pressure of the liquid column, and this kind of problem comes. It's very common. Okay. See, a liquid X means this of density 3.36 gram per centimeter cube is poured in a U tube in right arm with a height 10 centimeter. Okay, a liquid of density is poured in a U tube in right arm with height 10 centimeters. So means this is the liquid. This is the liquid X, right? Which contains mercury. So this is mercury. This is mercury. Another liquid Y is poured in the left arm with height 8 centimeter. Upper levels of X and Y are same. So mean this level is same. What is the density of Y? Okay. What we have to find out? Density of Y. The key thing is the upper levels of X and Y are same. Means the pressure at this is same. Now see, this is 10 and this is 8. So there must be, if I try to draw it once more, the U tube, right? This level is same. This is 10. So if this is 8, 8 will be somewhere like this, little bit above, right? So now pressure at the same, at one level is always same. So if this is same, so this is atmospheric pressure. So we can say pressure of this column of liquid X, pressure of this column of liquid X will be equal to pressure of this column of liquid Y plus 2 centimeter of mercury, right? So we will be trying to equate these two, right? So for X, first of all, what will be for X? Let's find out the pressure. For X liquid, what is the height? It is 10. H means height is 10. Rho, what is the density? What is the density of liquid of X of density? 3.36. So density is 3.36 gram per cc. Here the height is also 10 centimeter. The units are in the same same system. 10 H rho into G, let us just say G, is equals to H rho G, that is pressure by this liquid column, that is Y, plus this is 8, this whole is 10, so this will be nothing but 2. Understand? So this will be, so liquid column of Y, what is the weight? 8 into the density we have to find out. So let that be, say, rho Y into gravity plus, for mercury it is 2 into, for mercury you know, mercury you have to remember, in fact 13.6 gram per cc is 13.6 into G. Okay, so see, G all cancels out. Now we have to calculate little bit. So we can say 8 into rho Y. I'm doing 8 into rho Y is equals to how much? 10 into 3.36. That is 33.6 minus 2 into 13.6. That is 27.2. 27.2. So 33.6 minus 27.2, this will be 4, 1, 8, this is 5, yes, 5.4. So rho Y will be 5.4 divided by 8. It will be nearly somewhat like this, 0.8 gram per cc. Just check whether calculation is okay, right? Just check 10 into 3.36 into gravity. This will be equals to, right, 2 into 13.6 into gravity for this, and 8 into rho Y into gravity. This equation you need to understand, and calculation just check at your home, right? Understood? The concept is clear. So this kind of problem is a very essential kind of problem, right? Similar kind of problem I'm discussing. There is a YouTube, you will see, it is having mercury, right? You're pouring in water in one arms. What happens after the water is poured? You will see this mercury has raised up, and this is the water column, right? So now you have to balance. You have to see, I mean, how much mercury has raised up, what is the height of the water column. So this kind of problem, you have to basically use H rho G formula, and like you have to have one place where the pressure is same. That there should be one reference line by which you can equate the two arms in terms of pressure. Jaise we have done here. Clear? Okay. We are moving on to the next question. What happened? Okay. This is a very simple question. It's basically more of theory, right? Just read the question, you will understand. A lead shot of 1 millimeter diameter falls through a long column of glycerine. So of which chapter? It's nothing but viscosity, and we're trying to find out the terminal velocity. The lead shot falls through a long column of glycerine. So when it falls through a long column, what happens? Like as the velocity goes on increasing, As the velocity goes on increasing, the viscous drag, the viscous force, which is proportional to the velocity, that also increases. So a certain point is reached, what happens? Then that is the weight or the force with which it is falling down, there is a weight, is balanced by, one is a viscous drag, what I have told, and also the upthrust. The upthrust, it remains same throughout because it depends on the volume, but the viscous force, it goes on increasing. Why? Because as the velocity increases, viscous drag also increases. So finally, what will happen when the weight and the upthrust and the viscous drag, the upthrust and viscous drag when balances the weight, so there is no force, right? The body goes on falling at the same speed. So just you have to find out the graph. What will be the graph? So as it is reaching the terminal velocity, it means the velocity will be constant after a certain time. So yes, for a certain time, velocity will reach a constant, which is the terminal velocity. Clear? Okay, now we have come to another topic, the surface tension of surface tension. Calculate the force required to separate a glass plate of area 10 to the power minus 2 meters square with a film of water 0.05 millimeter thick. Surface tension is given by 10 to the power minus 2 meters square. So to separate the glass plate with a film of water. Okay. Calculate the force required to separate the glass plate of area with a film of water. Means you can think there is a ground, right? There is a film of water and there's a glass plate above it. So you have to draw it and you have to remove this. It's nothing but the surface tension. Okay. Now the surface tension is pulling this glass plate towards itself, right? Okay. Now, how do you find out what is the formula of surface tension? Surface tension, you know, is nothing but surface energy divided by the cross-section area. Now, how will you find out the surface energy here? Surface energy is nothing but, right, the force into the force which is unknown. Calculate the force, F. It is F into what is by what distance it has to move. It's nothing but the thickness, right? That is D. Say 0.05 millimeter thick. So it is nothing but D. Say D. This is D, right? Divided by the area. Divided by the area. Now see one thing. When we talk about like the force, we have to calculate the force. The force is area divided by this distance D. Now, for this distance D, right, there are two surfaces. One this surface and this surface, right? So, what we have? We don't have only one area, single area. Because when you're removing this area as well as this area, both need to be drawn together. So it's basically, it is not A. This A should be changed to twice A. That is T into twice A by D. So this is the force. And we have the values given. Surface tension is given by 10 to the power minus 2. I'm writing it once more again. F equals to 2 TA by T. 2 into 10 to the power minus 2. Right? Area is given 10 to the power minus 2. And the distance is how much? 0.05 millimeter. 0.05 millimeter is how much? 10 to the minus 3. Right? So it becomes 2 into 0.05. You can write 200 by 5. This is 10 to the power minus 1. So 200 by 5, it is 14 to 10 to the power minus 1. It is 4. There is some mistake, I guess. let me just see. Area is 10 to the power minus 2. Surface tension of the water is given by 10 to the power minus 2. So surface tension 2 into 10 to the power minus 2 into area is 10 to the power minus 2 divided by 0.05. Yes, it should be coming like this. 200 divided by 5, 10 to the power minus 3, it is 10 to the power minus 1. 200 divided by 5, it is 40. It's 4, somehow 4 is coming. Okay, just note down this problem, right? Maybe some calculation error is there, or maybe some part is, the values given are, they are wrong, they can be, might be. But the basic concept will be like this. When we have to calculate the force, right, we know the surface tension is nothing but surface energy by area, surface energy force into displacement by area, and but this area what we have taken twice this area, right? Just check. Okay, fine. We're moving on to the next question. Okay, now we are coming on to the thermal properties of matter. For thermal properties of matter, it's a very simple question. On a new scale of temperature, which is linear and called W scale, the freezing and the boiling points of water are 39 degree W and 239 degree W. What will be the temperature on the new scale corresponding to a temperature of 39 degrees Celsius on the Celsius scale? So on the Celsius scale, we are measuring 39 degree. What will be the value in the new scale? So when we compare, what we do, like if 39 is in the Celsius scale, what we do, like suppose there is a thermometer, right? Now this is the 0 point and this is the 100 point. That is the freezing point and this is the boiling point. If we take this to be my temperature, mercury is nothing but it is a material which have the expansion is proportional to the temperature, not the value we have chosen. So this ratio by this ratio remains the same. Like A length by B length remains the same. So for Celsius, what we can write? For Celsius, the temperature is 39. So 39 minus 0 divided by this ratio, 100 minus, 0. This is 0 only. (100 minus 0). Here, if you have to find out the temperature, suppose the temperature is W in the W scale. W minus W, here it will be W. W minus, here with the same, it is 39 W, it is 239 W. And this is W, right? So W minus 39 divided by 239 minus 39. And if you calculate, see it's looking very confusing. But 239 minus 39 is nothing but 200. This is 100, right? So 39 by 100 is equals to W minus 39 by 200. This becomes 2. If you just calculate, you will find out W very easily. I'm not proceeding. Fine. Okay. Now I think this will be the last question for today, as we are already almost time. This question is on thermal conductivity. See, in the diagram, a system of two metals, this one and this one, of equal lengths are equal, and the same cross-section area are joined together. What is the temperature? This is 300, this is 0. We have to find out the temperature of the junction. This is very simple application of the formula. You know the rate of heat flow is nothing but, right, is given by thermal conductivity K, A theta 1 minus theta 2, means the temperature, if this is the block, if this is temperature theta 1, theta 2, divided by D. A is the cross-section area, D is the length. So how will you use this? See, only thing is that here the thermal conductivities are different. One is K, one is 2K. So for the first one will be, and the heat flow in a steady state, the heat flow through the metals is the same. So heat flow through the first metal is nothing but K A is 300 minus, say this temperature is theta, divided by length is D, right? It is said equal length and equal cross-section area. So A and D will be same, but in this metal the conductivity is 2K. It is 2K A theta minus 0, right? This is theta minus 0 divided by D. It's very simple. So D, D, K, A all cancels out. So it becomes what? 300 minus theta equals to 2 theta just. So 3 theta equal to 300. Theta is nothing but 100 degrees Celsius. Understood? So this kind of simple problems you have to solve in NEET, right? Because of time, I couldn't finish. Like for radiation, there could be more problems on Bernoulli's equation. Bernoulli's equation applications are very simple, they are very interesting, right? So many topics are there, and also like for terminal velocity, there is also another thing called capillarity, right? So first get the concepts clear and go on solving this kind of problems. Another thing is how fast you can approach, how can solve the questions, right? I hope these classes are really helping you. Keep learning. Best of luck for your preparation. Thank you.